Welcome to the deep dive. Robots are getting seriously impressive. They can see, they can navigate complex spaces, pick up and put down rigid objects pretty easily now.
Yeah, they really are.
But there's this one, quintessentially human skill that remains a huge hurdle for them. Touch. And not just feeling something, but feeling precisely how much force to apply. Especially when you're dealing with things that are fragile or, uncertain.
Absolutely. Think about tasks you do every day without even thinking twice, like picking up a ripe peach without bruising it.
Right.
Or carefully separating maybe just one flimsy plastic cup from a stack.
Oh, yeah, that's a good one.
Or handling soft food. We're constantly using this incredible fine-grained force control. We adjust our grip pressure in real time based on tactile feedback we barely even register consciously.
Yeah.
And for a robot, trying to replicate that gentle adaptive touch is, well, it's incredibly hard.
It really is, and that's exactly the challenge a fascinating new research paper is taking on. It's called Feel the Force, Contact-Driven Learning from Humans.
Feel the force. Nice.
Yeah. So our mission in this deep dive is basically to unpack their approach. The core insight here, the big idea, is figuring out how to teach robots this delicate force control by learning directly from what a human hand feels and does.
So let's dig into why this is such a tough problem for robotics in the first place.
Okay.
Most traditional robot manipulation, it relies really heavily on vision, right? The robot sees where the object is, maybe estimates its shape, and then it executes some kind of pre-programmed grip or movement, or maybe it uses simple force thresholds like grip until you feel some resistance.
Right, like a basic safety stop.
Exactly. But that just doesn't work for things that deform or are fragile. If you just grip a soft loaf of bread with a fixed force or, keep closing until you see it start to squish.
Too late.
You've already failed. Exactly.
Yeah, because the human hand isn't just running a pre-planned script.
Yeah.
We're sensing texture, slipperiness, how something's squishing,
Deformation, yeah.
and crucially, the exact contact forces. And we feed that back into our motor control loop instantly, nanosecond by nanosecond.
Robots typically lack that really high bandwidth, responsive, tactile control system.
So what have people tried before? I know teleoperation is a thing.
Yeah, previous attempts to add touch have limitations. Teleoperation, where a human wears a haptic glove or something and remotely controls the robot.
Right, you feel what the robot feels.
Exactly. It gives the human the feel, which is great, but it's just not scalable for automation, You need the human in the loop constantly.
Makes sense.
Other methods try to guess the force needed just from visual cues, like watching how much an object deforms on camera.
Yeah.
But that's often not precise enough, not for genuinely delicate tasks where a tiny bit too much force is a disaster.
So this paper's approach, Feel the Force, or FTF, they're trying to sort of bypass those issues.
Exactly, by going straight to the source, human expertise, including the sense of touch. Their core idea is to learn this force-sensitive manipulation directly from human demonstrations that explicitly capture tactile information alongside the usual movement and vision data.
And the advantage there is.
The benefit is you leverage all that human intuition for delicate tasks, without needing these really complex haptic teleoperation rigs or spending ages collecting massive amounts of slow, expensive robot training data where the robot keeps failing.
Okay, that makes a lot of sense conceptually. But how do they actually capture that human feel and then, translate it to a robot? What's the actual setup look like?
Okay, so it starts with data collection. The human demonstrator wears this custom tactile glove. And this glove isn't just tracking motion like some gloves do. It has special magnetometer-based sensors. They're positioned really strategically on the underside of the thumb.
Why the thumb specifically?
Well, think about how you grasp things. A lot of the critical contact, the fine control, happens right there between the thumb and fingers. So they put the sensors there to capture those crucial contact forces.
Smart. And they pair that with vision.
Yep, just standard cameras, 2 of them capturing video of the human hand doing the task and the objects in the environment. And the key is that the force data from the glove is then carefully synchronized with this visual data.
So you get this really rich record. What the human saw, how their hand moved, and exactly how much force they were applying at any given moment.
Precisely.
Okay, so that's the human side. How does the robot side mirror this?
So they use a pretty common robot platform, FrancoPanda ARM. You see those a lot in research.
Yeah.
But here's the clever bit. They modified the gripper. They used custom 3D printed fingertips and mounted similar tactile sensors onto one jaw of the gripper.
Ah, so it's sensing in a similar place to the human's gloved thumb.
Exactly. It creates this direct correspondence, this sort of analogy between the human sensing area and the robot's sensing area.
Okay, that's neat.
Hmm.
So you've got the human data motion, visual context, force, and a robot with a matching sensor setup. How does FTF actually bridge that gap? How does the robot learn from the human?
Right. So the FTF framework takes all that human data and maps it onto the robot. They use computer vision techniques, pretty standard stuff now, to extract hand key points from the human video.
Like tracking the joints of the fingers and palm.
Exactly. These key points represent the human hands movement, and they get translated into desired positions and orientations poses for the robot's end effector, its gripper.
Okay.
And of course, the force data from the glove is bundled in with this demonstration data. They also track the objects in the scene using visual key points too, so the robot knows where things are.
And then some kind of learning model figures out what to do with all this input.
Precisely. A learning model in this paper, they used a transformer architecture, which is very popular for sequence data.
Right.
This model processes all this combined information. So the visual key points of the robot and the objects, the robot's current gripper state, like how open or closed it is, and crucially, the force readings that came from the human demonstration.
Okay, now this is where it gets really interesting for me. What does this model actually output? Is it just predicting, like, the next robot joint angles or where the gripper should move?
No, and that's the real novelty here. The model doesn't just predict where the robot should move, or just a simple open or close command for the gripper.
Okay.
Its main output is a prediction of the desired contact force at each step of the task.
Wow. Okay.
It learns the appropriate force profile for the task based on the visual context and what it learned from the human's demonstration, including their force usage.
Ah, so it's predicting, okay, right now, doing this part of the task, you should be feeling this much force. How does the robot actually achieve that predicted force? It can't just wish for it.
Right. This is the second critical piece of FTF.
Yeah.
At runtime, when the robot is actually doing the task, they use an intelligent controller on the robot's gripper. Specifically, it's a PD controller, but it's tuned for force control, not position control. So instead of just closing the gripper to a specific learned position,
Like most grippers do.
yeah, instead of that, this controller constantly monitors the actual force being measured by the robot's own tactile sensor on its gripper jaw,
Okay.
and then it continuously adjusts the gripper closure, opens or closes it just slightly, trying to match the desired force that the learned policy predicted for that moment.
Whoa. So the robot isn't just blindly moving based on vision. It's actively feeling with its fingertip sensor and adjusting its grip force, like on the fly, to hit that tactile target it learned from the human.
Exactly. That sounds incredibly powerful for delicate tasks.
It is. It closes that feedback loop. The high-level policy, the transformer, predicts the target force based on the scene and the learned-to-human strategy.
And then this low-level controller makes sure the robot actually feels that force or tries its best to by dynamically adjusting its grip.
Okay, theory sounds great. Let's see how this actually played out. How did they test FTF? What did they make the robot do?
Right, the real-world test. They put the Frankopanda robot with its tactile gripper through a series of pretty challenging manipulation tasks on a tabletop. And these tasks were specifically chosen because they are known to be hard for robots, precisely because they need careful force control.
Okay, give me some examples. What were these tasks?
Well, they included handling delicate food items, things like placing a piece of soft bread onto a plate.
Oh yeah, easy to crush.
Totally. Putting an egg into a pot, placing a bag of chips, you know how fragile those are, onto a plate, all without crushing them.
Okay, makes sense. Any others?
Yeah. They also had tasks requiring really careful isolation, like that plastic cup example, unstacking just one flimsy plastic cup from a stack without lifting the others.
Tricky.
And another one needing both force and dexterity, twisting and lifting off a bottle cap. You need enough force to grip and twist, but not so much you crush the cap or lift the whole bottle.
Those are absolutely perfect examples of where human touch is just key. So the big question, how did FTF do across these 5 tasks?
The results were actually quite compelling. FTF achieved an overall success rate of 77% across all these different delicate tasks.
77%. That sounds pretty good for these kinds of challenges. How did that compare to, other ways of doing this?
Yeah, they compared FTF against several baselines. These included methods that might use tactile information but more passively, or maybe just learn basic gripper open-close commands from human demonstrations or even from robot teleoperation data.
Yeah.
FTF significantly outperformed these baseline methods.
Can you give us a specific example? Where did FTF really shine compared to the others?
Sure, that unstacking task with the flimsy cups is a great illustration.
Okay.
The baseline methods, they often struggled to pick up just one cup. They'd either apply too much force and grab the whole stack, or not enough and fail to lift anything.
Right.
FTF, because it was using that force-aware control, learned from the human, showing how to gently engage and pull just one cup away. It was uniquely able to reliably unstack only the top cup.
That's impressive. What about the fragile food?
Similar story. For the delicate objects like the bread or the eggs or the chips, baselines that just relied on simple learned gripper positions or basic force thresholds often crushed them. FTF's active force control, aiming for that gentle target force, prevented that damage.
Now, it's interesting you mentioned baselines trained even on robot teleoperation data. You might intuitively think that training on data coming from the actual robot would be more effective than data from a human wearing a glove.
You might think so, but that's what was surprising. FTF, learning purely from these human demonstrations with a relatively simple glove setup, it often outperformed the baselines that were trained using robot teleoperation data.
Really? Why do you think that is?
Well, it suggests that even with maybe a simpler sensing setup like the glove, these natural human demonstrations captured the essential tactile intent and the strategy for these tasks remarkably well. The human instinctively knows how to apply force correctly, and FTF seems good at extracting that, maybe even better than just recording the robot's own movements during teleup. It makes human data look like a very effective source.
That's a really powerful argument for learning directly from people.
Mhm.
Okay, so it works well on the tasks. Did they test how robust it is? Like, what happens if things go a bit wrong during the task?
They did, yeah. They did a robustness test specifically on the chip bag task. While the robot was trying to pick up and place the bag, they actually physically disturbed it.
Huh, like poked it.
Yeah, pressing on it, holding it slightly, rotating it, basically messing with the forces the robot would expect to feel.
Okay, simulating real-world messiness.
Exactly. And even with these unexpected changes in the force profile, FTF showed pretty good resilience. It still achieved a 67% success rate under these disturbances.
That could adapt.
It demonstrated an ability to adapt its force control based on the actual unexpected forces it was encountering, which is crucial for the real world.
That's a very good sign. Was there any other finding from the experiments that, stood out to you?
Yeah, there was one specific experiment that was quite revealing, I thought. For the bread lifting task, they trained a version of FTF where they deliberately didn't feed the human's glove force data into the learning policy during training.
Wait, so the policy only saw the visual data and the human's hand movements? No force info during training?
Correct. Only visual and kinematic information went into the policy learner. The force sensor on the robot was still used by the controller at runtime, but the policy itself wasn't trained on the human force data.
So still figure out the right forces to use.
Yes, that was the cool part. It could still predict the desired forces reasonably well and perform the task successfully, placing the bread gently.
Wow.
Well, it implies the learning policy isn't just doing a simple, direct mapping like human felt X force, so robot should apply X force. It seems it's also learning to infer the necessary forces implicitly, just from the visual context and the way the human moved their hand.
So it's like it learned, oh, that object looks like bread, and the human moved this gently, therefore I should apply very little force.
Something like that, yeah. It's like it develops a kind of visual understanding of softness or fragility, which then informs the force controller about what's needed, even without explicit force training data for that specific object.
That's fascinating. It suggests a deeper level of understanding.
Right.
Okay, so this FTF approach is clearly a big leap forward.
Mm-hmm.
But no research is perfect.
Mm-hmm.
What are the current limitations they acknowledged in the paper?
Sure. They mention a couple of areas for future work, which is standard. One is about the sensors themselves.
Okay.
The current tactile sensors they used, both on the glove and the robot gripper, they kind of aggregate different force components together. So shear forces, which are sideways forces, and normal forces, which are crescing forces. They're measured together.
And that's a problem because...
Well, you lose directional information about the force. For even more complex, intricate manipulations, maybe sliding something carefully or twisting something with a specific grip, knowing the direction of the force might be really important. Separating out those shear and normal force components could be a valuable next step.
Makes sense. Anything else?
The other main point was about the data collection setup.
Right. The cameras and glove.
Yeah, the current setup relies on fixed, calibrated cameras to track the hand and objects accurately. This kind of limits the flexibility of where you can collect these human demonstrations. You need that controlled environment.
So not easy to just record someone doing chores around the house, for example.
Not with this exact setup, no. So future work could definitely explore using more mobile or flexible setups, maybe cameras worn by the human, like egocentric vision,
Uh-huh.
or perhaps better stereo vision systems that don't need such precise calibration beforehand.
Yeah.
Things that make data collection easier in more varied, less structured environments.
Okay. So while there's always room to improve, particularly on the sensing detail and setup flexibility, this FTF approach feels like a genuinely significant step forward in robotic dexterity, doesn't it?
It absolutely does. I think FTF represents a really fundamental shift by directly tackling this challenge of teaching robots delicate force control and doing it using natural human examples by learning not just where to move, but the required tactile interaction, the right force. Robots can suddenly gain the ability to perform a vastly wider array of these everyday tasks that just require that human touch intuition.
And that ability to learn these nuanced skills from relatively easy to collect human demonstrations.
Yeah.
I mean, easier than complex programming or millions of robot trial and error attempts.
Right.
That offers a truly scalable path towards more capable and versatile robots in the future.
Definitely. The exciting part for me is thinking about how much more capable a robot becomes when it can truly feel the world it's interacting with, when it can adjust its actions not just based on what it sees, but what it physically senses through touch.
It really changes the game. So maybe a final thought for everyone listening. If robots can eventually handle anything from a fragile piece of fruit to sensitive lab equipment with the same gentle precision as a human, what new areas of automation suddenly become possible?
Good question.
What could this mean for things like elder care or food handling in restaurants or factories, delicate assembly lines, or maybe even just, finally getting a robot that can reliably help out with chores at home without breaking things? How does adding this missing sense of touch really unlock a whole new level of robotic capability that maybe we've only just imagined before?